All right, guys, let's begin the lesson. Turn on the cameras and let's talk. So the derivative of y equal to x to the power of a. The derivative is what? The derivative is clearly just your regular situation where a drops down and it's x to the a minus 1. Agreed? Now the derivative of y equals to a to the power of x. What's that? Very good. A to the power of x ln a. So this is a to the power of x ln a. Good. Now please recall and take the derivative of x to the power of x. We did it last lecture. Very good, amazing guys. So good. It's x to the power of x ln x plus 1. You all remember how we figured this out? So we can set y equal to x to the power of x. Advise me please in the comments what would have been my strategy. What do I do? Y is equal to x to the power of x. I do what? ln. Very good. Very good. Do you see why I take ln, guys? Because if I take ln of y, that will allow me to drop the x. That's what it allows me to do. And then I convert an expression that I do not understand, and I bring the exponent down. And that makes it an expression that I understand pretty well. Very good, Francis. Yes, guys? And then you take the derivative, and it's just product rule. So the result is we have 1 over y prime is ln x plus 1. So y prime is simply x to the power of x ln x plus 1 as a result of multiplying by y, right? So I'm interested in only the derivative of this function. All right, guys, with the same successful strategy, please quickly calculate d. What's the derivative in d? Quick. Fast. Okay, good. Good. And if you are done with some of them, continue, of course, to the next question so that you don't waste time, guys. Do the questions that are there. Very good. Okay. Right, guys, show up your pretty faces. It's boring. I have fewer and fewer people showing their faces. You are trying to make me blind or something? Cameras on. Good, thank you. Jet, Nashin, Francis maybe. I haven't seen you in a while. I need to remember what you look like. Anna, Zayed, Zakaria. Come on. All right, so here is the calculation. For this expression, I can just simply say, I can say ln of y, where y is this expression, equals to sine x ln x. And then the derivative of y prime will simply be, I just will move the y across, it would be x to the power of sine x multiplied by derivative of sine, which is cosine x ln x plus sine x over x. Good? Same goes for the remaining questions. So for instance, what is the derivative of e to the power of x? We already know the derivative of x to the power of x. So the result would be e to the x to the power of x multiplied by x to the power of x times ln x plus 1. Agreed? You can, if you want, to drop this parenthesis. It's not needed. This is the result. That's for e. Now f, I am not even gonna go through because it's the same idea. Do you agree? Or do you need me to go through? Is there anything confusing about f? It has an extra logarithm. So what's the result? The result is that you have that ln of y is equal to cosine x ln x. Yes? ln of ln x, my apologies. Ln of ln. So the derivative is simply minus sine x. Then we have times ln of ln x plus cosine x 1 over ln x times 1 over x. And then you just multiply this entire thing. So the full result is this expression multiplied by ln x to the power of cosine x. Now let's move on. Guys, now we begin the topic of derivatives of inverse trigonometric functions. Would you please tell me, do you think trigonometric functions are invertible? Is sine x an invertible function? Would you help me please figure this conundrum? Is sine x an invertible function? And be careful before you say something. Is sine x a reversible function? Because I say, and you might have said, because I'm calling the topic derivatives of inverse trigonometric functions. Yes, you think I'm revealing that it's invertible. Think about it for one moment, guys. And the answer is no. Sine is not an invertible function. Why? Just because I look smart and I say, let's calculate derivatives of inverse functions that make some sense. Sine is not an invertible function. It does not pass the horizontal line test. Do you see that? Here is a picture. Here is the curve sine x, and you can see that if I draw this green horizontal line, it intersects the curves multiple times. Do you understand what that means? That means that, because think about it, that means that a given input of sine cannot be retrieved. Let's say you see where I place this star, right? This blue star. So here is a point where this blue star is mapped to, and it also, so this corresponds to this y, right? Now if I have this y, now and I want to know how that y was manufactured. It could have manufactured at this point. It could have been manufactured at this point, at this point, at that point. So most points have infinitely many all of them have infinitely many possibilities, to be precise. Do you agree? Every single point on the y-axis that can be manufactured could be manufactured out of infinitely many inputs. Are you with me? Do you understand the essence of the horizontal line test? The horizontal line test is showing you whether or not you can undo the operation. Now, to undo the operation, you need to know what was the factor that brought it to the condition where you have, but this information is lost, right? So if I take the input into sine and I produce a y, that y could have been produced with other inputs. Do you understand? It's like if I know that John pressed on button number 1 and there was a soda can produced, Coca-Cola, right? Then I can take the Coca-Cola and say, oh, John was the person. Right? But if John, George, Albert, and other people pressed on that same button and produced Coca-Cola, I don't know if the Coca-Cola should be manufactured back into John or into Albert or into all the other people that were the inputs that produced this output. Do you understand? I do not know how to undo it. Confirm by writing yes that you understand me, or writing no if you fail to understand me. I would then try to re-explain. Completely clear, yes? Should be absolutely clear, guys, if you understand what inverse functions are doing. So inverse functions are not invertible. I mean, they don't exist, to be precise, for trig functions. So how am I going to take derivatives of such functions? What am I saying? Well, this is what we are going to do, guys. Do you see this curve that I covered in red? Right, so I'm going to define capital sine x, and capital sine x, it's known as a branch of the sine function. Branch because you could have selected other segments. So I am restricting the domain of my function from minus pi over 2 to pi over 2, because over that region, basically, if I also know that my input came from this region, then each input corresponds to a unique output. Do you understand? Right? If I additionally say that that my input that produced this y that I'm trying to reprocess back into what it used to be, if it came from minus pi over 2 to pi over 2, that means that input is reversible. It's in one-to-one correspondence. Do you see that the horizontal line intersects the curve colored red only once? Do you follow? So although the global sine function is absolutely not invertible, the local sine function is very much invertible. Yes, which you usually don't make a distinction between them in calculus, but if you want to, you can think of it as capital sine of x. It's a sine with restricted domain. So this is what we would say. Capital sine x is the same as original sine, but the domain is restricted, and that makes this function invertible. Okay, and we will stop beyond that point, stop using the capital sine notation. Just remember that when I speak of inverse functions, I'm not speaking of global sine, I'm not speaking of global cosine, but I'm speaking of those functions restricted to a region that makes the function invertible. Good? Now, with this, guys, you are first going to calculate sine inverse of 1. Again, I want answers in radians. We forget the degrees are not very natural. We want answer in radians. What is sine inverse of 1? The inverse, so what does sine do? It converts angles to the length of the vertical rope, if you remember what I mean by a vertical rope in my crane, right? It calculates the length of the opposite side to the angle in radians. So what is sine inverse of 1, please? In other words, this is asking what input into sine produced the number 1? What must have been the input to produce 1? Another way of asking it, a sine of what is equal to 1? Very good. The answer is clearly pi over 2. So the answer here is pi over 2. Let's write it over here. Sine inverse of 1 is pi over 2. Do you agree? And why I cannot, I mean, there are other values that give us the same result. I mean, if I add 2 pi or 4 pi or 6 pi to pi over 2, sine of that would also be 1. But in the domain between minus pi over 2 and pi over 2, there is only one unique value that produces 1. Yes? Similarly, please tell me what is the sine inverse of minus 1. Absolutely, it is minus pi over 2. You understand, guys, we're studying the same functions. I mean, maybe you think it's a new function that we're defining, but in many ways, I'm just talking about sine, but I'm talking in reverse. I'm changing my perspective. I'm saying the output was minus 1. What was the input? The ratio of opposite to hypotenuse is minus 1. Yeah? What is minus 1 radian, of course, right? So what is the angle? So the angle is minus pi over 2. Are you good so far? Yes. Now let's continue with the next. Please tell me what is sine inverse of root 2 over 2. You're supposed to know several angles and know how to get to them if you forget. Sine inverse of root 2 over 2, please. Very good. The answer is pi over 4. Pi over 4, yes. So we say that sine inverse of root 2 over 2 is pi over 4. Now help me with the next one. What is a sine inverse of minus 1/2? Very good, minus pi over 6, guys. You should be automatic with that. And if you forget, you should be able to construct the triangles just as we spent so much time on trigonometry. Remember, we spent, I think, what, 2-3 lectures on just understanding the basics of trigonometry. I hope it was not in vain. So this is minus pi over 6. Good? Let's continue this game. Sine inverse of minus root over 2. Root 3 over 2. What is that? Of minus. We place a minus there. It's with a minus, guys. Yes, so it is minus pi over 3. Yes? Minus pi over 3, guys. Now, another question here, and I want all of you to think, what is sine inverse of 5? What is that? Sine inverse of the number 5. Sine inverse of 5, guys, please, is what? What value does sine map into 5? I want to see lots of answers and they should be cascading. What value does sine map into 5? Exactly, finally, undefined. Right? Sine, do you remember the crane? We played the animation. Have you seen the rope? Can the rope be longer than the crane? Can the side of the triangle be longer than the hypotenuse? No, it cannot. Yes? It's undefined. Do you agree? Of course, guys, that's in at least not in real variables, right? So there is a different story for complex variables, right? Those functions are more complicated. Undefined. For which values, please, may I ask sine inverse? What are the values for which I can ask sine inverse? Write me in the interval notation, please. Yes, finally, -1 to 1. Yes? Sine cannot produce values that are bigger than 1 or smaller than -1, but can produce all the values in between as it is continuous, right? If you can produce the value 1 and you can produce the value -1, you must be able to produce all the values in between. Do you understand? That's by intermediate value theorem, guys, because sine will then stretch a graph, a thread between -1 and 1. All those values are possible, nothing else is possible. At least not for real values, not for real numbers. And now, guys, it's your turn. Now you see, guys, I'm gonna ask you a very old question. You're going to calculate sine inverse for me, please. Derivative of sine inverse, to be precise. Right? Let's see how we do that. So I want you to tell me what's the derivative of sine inverse x. I want you, okay, good. So what will you do to obtain this derivative? You understand the question, guys, right? Because it's the same curve, you're really just looking at it from a different perspective and calculating the slope of the tangent line. So it should not be difficult. Very good. Very good. So here's how we begin this, guys. It should take you a second to calculate. So y is sine inverse x. So applying to both sides sine of y equals to sine inverse x, which is x. You understand, guys, what is the sine y equals to x stuff? It just means that I am now doing this. You see what is it? What is this implicit differentiation really telling me to do? It tells me to take my head and place it horizontally, so that the x-axis looks to me like it's a vertical axis. Do you understand? And if I do that and look horizontally, which is now my up, I'm seeing the original sine curve, right? So, and I already know how to take the derivative of that. So then take the derivative of that expression, you get cosine of y times y prime equal to 1. And so y prime is equal to 1 over cosine of y. Do you see why it's 1 over? The 1 over is because it's the same slope as I had before. Same exact slope I had before, but I need to, how should you say that? Same exact slope I had before, but I need to take 1 over it because I switched the notion of vertical and horizontal. Yes? So it's cosine of y, which is 1 over cosine of sine inverse x. I could leave it like that, but I can do something much better and much more useful. I am going to try to evaluate cosine inverse of x. Cosine of sine inverse of x. Yes, guys? So what's the situation? Sine inverse of x. How am I to understand this in terms of a triangle? Here is a triangle, right? Here is sine inverse of x is an angle. And this is saying that if you take sine of that angle, you would get ratio of opposite to hypotenuse equal to x. Do you understand? Look, think about it again, guys. Sine inverse of x means I am the angle that if you apply sine to me, you will get x. It's an angle, apply sine to this angle, you will get x. But if you apply sine to an angle, you take ratio of opposite to hypotenuse, yes? Now, that means that opposite is x, hypotenuse is 1. Any other choice, it could be opposite is x squared, the hypotenuse x. Any other choice produces a similar right triangle. Do you understand? Any choice you would have this ratio would produce similar right triangles. So 1x, and then the remaining side is root 1 minus x squared. I just complete the triangle using Pythagoras theorem. Are you with me? Now, if you are with me, please tell me what is cosine of sine inverse of x. So that means this is 1 over what? What's cosine of sine inverse x, please? Cosine of sine inverse of x, you look at this triangle, guys. The information is right here. Cosine of sine inverse x is no, that's sine of sine inverse x. Look at it. Sine of this angle is opposite to hypotenuse. You see, guys, your problem is that you're not interpreting the symbols. They're meaningless to you. Right? To me, they are not. I mean, I have a very clear understanding of what it means. So sine inverse of x is an angle that if you apply sine to it, you get opposite over adjacent equal to x. Sorry, opposite over hypotenuse equal to x. Which means that's how I set opposite x and hypotenuse 1. Do you understand that any other choice will produce an equivalent, or better said, similar triangle? Yes, so I might as well use my choice x as opposite and 1 is hypotenuse. By Pythagoras theorem, the adjacent side is then hypotenuse squared minus opposite squared to take the square root of that. So it's root of 1 minus x squared. Agreed? Yes? And so please help me. What is cosine of sine inverse of x? What happens if you apply cosine? What is it that you do? If you take cosine of an angle, you take what, please? Adjacent over hypotenuse. You memorize this who knows how many times. So you take adjacent over hypotenuse. So what is cosine of this angle? Adjacent is this, hypotenuse is 1. So it will be root of 1 minus x squared. Yes? So that's how I get root of 1 minus x squared here. Do you understand what I just figured out, guys? It's a very, very useful and important derivative, is that the derivative of sine inverse x ends up being 1 over root 1 minus x squared. The derivative of sine inverse of x is actually an algebraic function. Okay, of course, everything is based off a triangle. The trig functions are related to what? They're related to circles, to ratios, to triangles. Yes? Now, if you understood, guys, I want simplified, in simplified form, please tell me what is the derivative of cosine inverse x. Calculate this one. Okay. All right, nice. Nice. So what do you do, guys? You set y equal to cosine inverse x, and so that cosine of y is equal to x. And so take the derivative of cosine, it would be minus sine y times y prime is 1. And so y prime is equal to 1 divided by cosine of, divided by minus sine, I'm sorry, of cosine inverse x. Everybody agrees with this calculation so far? Now, how do I simplify this thing, guys? So here I draw a triangle. I'm trying to understand what is cosine inverse. So I draw a triangle. And what do I do with this triangle, please? Very good. Very good. Cosine inverse is where I place it, yes. So you see, guys, this is my cos inverse of x. That means that this part is x and this is 1. Do you agree? You understand why horizontal is the x part? Because if I apply cosine to this angle, I will get x. But if I apply cosine to this angle, I get ratio of adjacent to hypotenuse. So this is what we have here. So 1x, and then the remaining part is root 1 minus x squared. Yes? So what do we now see? We now see that the derivative from this information is simply minus 1 divided by sine of this angle. Sine of this angle is root 1 minus x squared. Good? All good? Now, guys, next task. So we now know how to take the derivative of inverse sine and inverse cosine, correct? They're almost the same. Now, tell me, please, how to take the derivative of inverse tangent. Of course, guys, as I mentioned, with all those functions, they're not invertible, so you always have to pick a domain for those functions where the function then will become invertible. Yes, so you pick a domain for each of them. And I'll mention that in a moment. But calculate the derivative of tangent inverse. Well, when you think of those functions, Jahin, you of course have to know the domain if you're using it for something, right? I'm right now just playing with the derivative, and the fact that I don't need to know the domain to calculate it means something about any branch of tangent inverse that I can take. Branch meaning that there are many, many different tangent inverses that I can define, not one. Just like there are many sine inverses I can define, the one that we have defined is called principal. You understand? I mean, I could have selected the domain to be somewhere else. So restrict sine on a different domain, and I would have gotten a different sine inverse function. You see what I'm saying, guys? I could select for sine, I can select the domain between minus pi over 2 to pi over 2. I could have selected the domain to be the same, but shifted, let's say, to pi. So I could have selected the domain to be 2 pi plus pi over 2 to pi minus pi over 2. You see, I could shift the entire thing, and I would have a different function. Does anyone understand what I mean? No? I'll draw it in a moment then. Let's get back to this calculation. Calculate derivative of tangent inverse, and let's see. Okay. All right, guys, the same idea. Y equal to tangent inverse x, which means tangent of y is x. Agreed? Which means that the derivative is, if you allow me to skip, y prime is the derivative of the function I am interested in. It's 1 divided by secant squared y. Everybody agrees? Which is 1 over secant squared tangent inverse x. Correct? Now let's calculate what is secant squared tangent inverse x, please. So I am drawing myself a triangle. And here I place tangent inverse. Tell me what should I do next, please. Help me. Very good. Thank you, David. It's simply, if I apply tangent to this angle, look at the tangent inverse of x means apply tangent to this thing and you will get x. But how do you get x if you apply tangent? It's always opposite to adjacent, yes? So that would be x and 1. You understand, guys? I could have also selected x squared and x. It's just the ratio would always be the same and triangle would be similar. Right? And then the hypotenuse is what? The hypotenuse is square root, or in this case, of 1 plus x squared. So far clear? So what is secant squared? Secant squared is hypotenuse over adjacent, right? So hypotenuse over adjacent. So basically I have that secant of tangent inverse x. If it is squared, this is simply root of 1 plus x squared squared. So the result is 1 over 1 plus x squared. Agreed? Are we together, guys? We all understand? Ask me questions if something is not clear. Do you understand how I use the triangle? Why I use the triangle? Right? Because tangent inverse it just says the angle that if you apply tangent to will give you ratio x. So I draw a triangle and I see how I can get ratio x. It means opposite is x, adjacent is 1. Right? And I'm hoping you understand, guys, that there are other possibilities. Opposite could be x squared and adjacent then will be x. Opposite could be 2x and adjacent would be 2. It doesn't matter if it's just all of those are just rescaling of the same triangle, ratio will be the same. Trigonometric functions are only concerned about proportions in a triangle. So why is it 1 on the base and x on the side, Zakaria? Because tangent is opposite over adjacent. Yes? So we have tangent inverse of x. Apply tangent, you get opposite to adjacent. And you are supposed, but this is telling you if you apply tangent, you will get x. So I know that opposite over adjacent ratio is x. So if I say opposite is x and adjacent is 1, I achieve a ratio of x as required. Is this clear? Okay, guys? Good. Next question. I want you to please tell me what's the derivative of secant inverse x. Thank you, Humira. And Christiana. All right, so what's the answer, guys? The answer is all the same. We have that secant of y is equal to x, and therefore secant y tangent y prime is equal to 1. So y prime is equal to 1 over secant of secant inverse x tangent of secant inverse x. Yes, that's what we have here. Now we know secant of secant inverse x is simply x, right? So we have x tangent secant inverse x. Yes. So what's the situation? So the situation is as following. As follows. You draw the triangle. Here is secant inverse x. Please tell me where I place what. What sides do I label? There are two sides I can label, and the third side I calculate by Pythagoras theorem. Which sides do I label, please? Yes, thank you. X is hypotenuse 1 adjacent, which means this is now x squared minus 1. Yes? And so the result is 1 over x. Look at it, I calculate tangent here. Tangent is this side. So it's x root x squared minus 1. So this function is the derivative of secant inverse. Good? Here are, by the way, the domains of definition for cosine, secant, tangent, and cosecant. Those are the common domains. As I mentioned, guys, you have a lot of branches of the inverse function. So for instance, if I were to draw the full sine curve, something like this, right? So I have, this is my sine curve. Yes. So then the principal branch where I take the inverse is here. You agree? But I could have taken another branch. I could have decided to define it over here. Right? And I even could have decided to define it somewhere, let's say on this side. Maybe it's this. You agree that whatever curves I underlined, they are invertible. Right? So there are many, many inverse functions. This is the one that you call principal branch, but you have this function, right? You have the function. This is the function f of x. It's also an inverse. You agree? This f of x is an inverse of sine. If you take f of x and compose it, if you take f of sine x, you will get x. Properly defined, where the x is coming in here. Do you follow what I'm saying, guys? That there is no unique inverse. It's just the one that you're dealing with, typical one, was defined to be this capital sine inverse of x, and that's called the principal branch. This is the one that's defined over here. So this here is sine inverse x. But you could have defined others. You agree? You follow what I'm saying? I mean, I could have restricted my domain to be something else. So there are many, many inverse functions. Different regions produce the same thing, so there are different inverse functions for this sine curve, for its different sections, of course. Okay. Here I just mentioned the calculations of all those different various functions, guys. Here, very quickly, please calculate the derivative of tangent inverse squared. All right, so what's the derivative of tangent? You should do it in 2 seconds, guys. I don't know. Tangent inverse squared is simply, it's simply what? For A, this would be 2 tangent inverse x divided by 1 plus x squared. Because the derivative, remember, the derivative of tangent inverse x is 1 over 1 plus x squared. Yes? So just easy chain rule. Good? Now take the derivative of tangent inverse of x minus root of 1 plus x squared. All right, so what's the answer for this derivative? This is simply for b. The answer is 1 over 1 plus x minus root 1 plus x squared multiplied by the derivative of the inner function, which is 1 minus root 1 plus x squared, and here is an x. Yes? Now, some of them, of course, you right away can think it's useful to not just calculate the derivative, but figure what this thing is. So can you calculate number c, please? Yes, for the last one. Well, I did the chain, guys. It's a matter of practice. Solutions are here. Solutions are here. Here it is. Of course, I did it's chain rule. It's derivative of tangent inverse, then the derivative of what's inside. That involves chain rule. Number C. Interesting, Christiana. You got 0 for C. Let's see. Others, can you calculate faster, guys? It should not take you a long time. Okay, so the function again, I think, was cotangent inverse of t plus cotangent inverse of 1 over t. Am I right? Yes, I am. Now let me just see, guys, what you would say. So first of all, do you remember how to take the derivative of cotangent? So cotangent inverse of t, just by using the same ideas as before, if you take the derivative, you will find it is minus 1 over 1 plus t squared with respect to t. You follow? It would be having a minus 1, but aside from that, it's the same thing. You can just do the derivative by saying y equal to cotangent inverse, all that stuff. So it would be this expression. Now, what is cotangent inverse of 1 over t? Let's see. Take the derivative of that. You would get minus 1 over 1 plus 1 over t squared multiplied by minus 1 over t squared. Do you agree? Because derivative of 1 over t is minus 1 over t squared. So when you multiply the minuses, they go out. And what do you get? You get 1 over a multiply t squared through. It will be 1 over t squared plus 1. And so altogether, the derivative of cotangent inverse of t plus cotangent inverse of 1 over t is equal to minus 1 over 1 plus t squared plus 1 over t squared plus 1, which is 0. Yes? So I get 0. Now, would you please tell me that we're investigating, guys? I got 0. Could you tell me what it means about this function? I got the derivative of this weird function is equal to 0. What does it mean about this function, please? Think about it, guys. I took the derivative, if you understood conceptually anything throughout the semester. I take a derivative of a function and I get 0. What does it mean? I'm looking at the slopes and all the slopes are horizontal. All the microscopic line segments are aligned because the slope is everywhere the same and it's horizontal. Do you follow what I'm saying? Can you see it, guys? You see it, right? Not just me. Constant, right? Because what the derivative is talking about, it's talking about the orientation of the microscopic tiles that built up the curve. If there is a function, that means the tiles are moving around, right? They're differently oriented as I move through the curve. That makes it a curve. If it's the same number, if it's a 5, it means that all of them are aligned this way at an angle that makes it 5. If it's 0, then all of them are aligned like this. It makes the function constant. Do you understand? So that means that cotangent inverse of t plus cotangent inverse of 1 over t is a constant. Is it weird, right? There is no t that actually is doing anything. Yes? The t here is not doing too much. So what's the situation if the t is not doing too much? It means, let's try to understand it by drawing a triangle. Well, horizontal asymptote is the limit as you go to infinity, right? That's something else altogether. Limit as x goes to infinity, the curve becomes horizontal. If that happens, then it's a horizontal asymptote. So let's try to understand what are the relations here, guys. So what's the relationship? So suppose that here I have a cotangent inverse of t. That means that this is t, and the opposite side is 1. Do you agree? It's t divided by 1. Yes? Now, in terms of cotangent, then what is this? What is this angle, guys? What is this? This is the same. Could you name this angle in terms of the ratio? What is this angle? So this angle is cotangent inverse t. What is this angle in terms of cotangent, please? Well, I mean, in terms of cotangent, this is cotangent inverse t, and what is this angle then? It is, look at it, cotangent is of an angle is adjacent to opposite. So this would be cotangent inverse 1 over t. And I am asked to calculate their sum. Yes? So tell me, please, if you understood what's cotangent inverse of t. We said it should be a constant, plus cotangent inverse of 1 over t. What particular constant is this equal to, please? Thank you. One person understands. What about the rest of you? Pi over 2, because the angles, this angle plus this angle adds up to pi over 2. So in fact, if I realized that identity right away, it would be no point to take the derivative. The derivative was obviously 0. Do you follow? Yeah, you should follow. The rest I'm leaving for you guys. You can deal with those questions. You can, of course, look at it, secant inverse x plus tangent inverse 1 over root of x squared minus 1. Those you should be right away suspicious. Maybe there is an easy way to do that. All right, let's continue. Finally, we are at related rates. This is a very difficult topic, and I almost feel it's pointless to teach it for you. Because in my experience, no matter if the previous material is not understandable, then this material people tend to make mistakes in this class with almost 100% likelihood. So this is the beginning of how this mathematics is applied in physics. So related rates are used all the time in mechanics or in physics, and I can show you afterwards perhaps why. Okay, so here is the situation, guys. So what we have is, imagine we have a very simplistic model of a tanker that is leaking oil into the sea. So the water is still, and the leaking is spread in circular pattern. Yes? So imagine you're watching a video of it. So here, as you move the time cursor forwards, you can see that the puddle of oil is growing to be larger and larger. Agreed? Now, what changes with respect to time? Which factors in this video change over time, please? And write it fast. The radius, correct. The radius changes as a function of time. What other properties here change as a function of time? So we have a circle growing, a radius changes. What else changes? Diameter. What else? Circumference, area changes, right? So all of those things, because they change with time, they are functions of t. Do you see why they are functions? I move the cursor anywhere, and r is a function of t, because there is going to be a definite radius at a definite time t. There is going to be one radius for every particular time t. Do you agree? So the radius is a function of time. The circumference is a function of time. You can see that this arc is growing. Right, and many other factors. Now, where is the idea of related rates comes from? Is that, of course, guys, because the pattern is circular, there is a relationship between the area that changes as a function of t and the radius that changes as a function of t. Do you agree that area is pi r squared? So the area, although it's a function of time, is also a function of the radius. So area of t is really pi of r of t squared. And similarly, so I related the radius and a. Two functions, I wrote them in an equation that relates one to the other. Circumference is 2 pi times the radius. Circumference can be also written as pi times the diameter. Area can be written as circumference squared divided by 1 over 4 pi. Because circumference squared is, circumference is 2 pi. Right, it's 2 pi times r, and area is pi times r, right? So here I need to remove the pi is squared, I need to remove a pi, and I need to remove a 4. Okay, so I can relate circumference to area. All of them are linked. So here is a first question. So suppose tanker is leaking oil at a constant rate of 2 meters per minute. Okay, its area 2 meters squared per minute. You understand? We're imagining a flat thing. So 2 meters. So in other words, if you were to observe the area, it's always growing at a rate of 2 meters squared per minute. In other words, in an extra minute, there is going to be extra 2 meters squared to the area. Do you agree? You understand? So I'm going to ask a few questions. Is the rate of growth of the radius increasing, decreasing, or staying the same? I just want to see what's your intuition. You understand? The area is growing every minute by 2 square meters. The circle is growing by 2 square meters every minute, constantly. In other words, in 1 minute, it will grow 1 square meter. In half a minute, it will grow, it would grow in half a minute, 1/2. Good? I mean, yes, well, you understand. In 1 minute, 1, in 1/2, so in 1 minute, 2, in 1/2 minutes, 1. My question is this. Is the radius growing at a constant rate? The radius is growing, you agree? Is it growing at a constant rate, or is it speeding up, or is it slowing down? The growth of the radius. So the spot is spreading. Is it going to spread faster? Is it going to spread slower, the radius? What do you think, intuitively? Okay, come on, guys. A lot of you should quickly write an answer. What's your intuition for such things? Area is spreading at a constant rate. Is the radius going to go faster, slower? Okay. Yes, the answer is, of course, slower. All right. So area is increasing at a constant rate, but that means that here I try to calculate very simply what's the difference in the radius growth, right? Because every 1 unit growth, so basically you see the radius is squared here, right? It's squared. You see, so if the radius doubled, for instance, right? If the radius is doubled, the area had to be quadrupled. But the area is increased at so basically, so you understand, but the area is increased at a constant rate, right? So every time you double the radius, you quadruple the area, right? So it should take longer time. You agree? Longer and longer time to quadruple the area. So the radius, if the radius was growing at a constant rate, doubling the time it takes to double the radius is always the same at any given moment. But each time you double the radius, you quadruple the area. So the radius has to go slower. So let's then now look at the next part. If the video starts at the moment of accident, in other words, where the tanker just begins to spill, give explicit formula for A of t and R of t as formulas of time. Can you do that? You understand what I'm saying, guys? So the video started at the moment where the area was 0. The area is increased at 2 meters per Second, I want you to figure out in terms of time the explicit formulas for the size of the radius and at any time t and the size of the area at any time t. Very good, Humira. Wonderful. Area is 2 times t. And thank you, Christiana. So the radius at time t, right? Here is the calculation, guys. Area is 2 times t. Do you understand why? As simple as that. At 0, we have 0 area. At 1 minute, we will have 2 square meters of area. At 3 minutes, we will have 6. You understand? At any t minutes, we have doubled in minutes area. You agree? And what is the radius? The radius is, so the r of t squared times pi equals to this number. So radius of t is the square root of a t over pi. So the radius is equal to the square root of 2t divided by pi. You see, you understand how I solved it, correct? You see how I obtained the formula for the radius, correct? It's very simply, I have that pi times r of t squared is area of the circle, so it's equal to 2t. So r of t had to equal to 2t divided by pi square root. Yes? So I was able to find explicit formulas for area. And then if I calculate explicitly the derivative of r, for instance, right? How fast is the radius changing? Look what happens. I take the derivative of this function of time, and that's root of 2 over pi times 1 over 2 root t, which simplifies to this, this is the formula, guys, you see? So the bigger the time, the slower is the growth of the radius. Do you see that? Because it's 1 over root of that time. So just as we expected, bigger time, slower growth. So we can, of course, guys, use implicit differentiation. Suppose this is the question, guys. How fast does the radius grow 6 minutes into the video? Question understood? How fast radius grows 6 minutes into the video? In other words, what we can imagine, guys, do you imagine what it means, the speed here? Imagine that the radius is attached a speedometer. Can you imagine that? As the radius is moving, the speedometer is showing how fast it's moving. So if I press pause 6 minutes into the video, in my pause, I theoretically can see the speedometer's arrow. I want to know how fast is the radius growing or moving exactly 6 minutes into the video. So if I press pause at 6 minutes, what is that speedometer showing, please? Calculate. I'll be back in a minute. I would like you to calculate what happens at 6. Hmm? Maybe I'll be back in 3 minutes and you'll tell me what happens in 6, okay? All right, let's do this together. It should be, still haven't seen the response here. I don't know why. Explicitly, guys, the derivative of RT. The derivative is, if you remember, supposed to tell me the speedometer. You remember that philosophy, right? Little change. If there's little time, there would be little change in speed. So the derivative is a perfect tool to calculate the speed of something moving. And the radius here is moving. Are you picturing it, guys? When I say calculate the rate of growth of the radius, I'm imagining, me personally, a speedometer attached to the radius. As the radius is growing, the speedometer is showing the movement of the tip of the radius. Yes, and what is that movement indicating? The derivative explicitly of RT is the derivative of this function, which is what we get here. And then I simply plug 6 minutes and I see that the rate of growth is root of 2 pi times 1 over 2 root 6 meters per minute. That's the rate of growth of the radius. Now here I was actually fortunate and able to calculate the exact formula in time for r. Just like with implicit differentiation, this very thing is very difficult. In most cases, it's very, very difficult to carry that calculation. So we are proceeding by implicit differentiation. Do you see, guys, that here I have a of t equal to pi r squared? Yes? And I simply don't like to write, look how much bulkier it looks. I'm simply writing a equal to pi r squared, but I remember that each side of the equation is a function of time. You follow me, guys? So then I take the derivative of both sides. You see, I take the derivative of a and I take the derivative of pi r squared implicitly. What do I get? I get that the a dt is, because this I don't have the formula for the function, so its derivative is the a dt. I forget that I can figure it out explicitly. The a dt is the derivative at some time t is equal to the derivative of this with respect to t, which is pi times 2r times the r dt. Yes? Which is what? I know that the a dt is at any moment of time. I'm told at any moment of time, the leak is happening at the same rate. Yes? So what do we get? We have that this number is 2. And what do we get on the other side? It's 2 pi r dr dt. 2 pi r dr dt. Correct? Do you understand where the dr dt comes from? Because we have r squared. We are using chain rule. And what is then the situation? Then the r dt is 1 over, look at it, I just move everything across, and the r dt is 1 over pi r. Yes? And then I just calculate when t is equal to 6, 6 minutes later, a is going to be equal to 2 times 6, which is 12. So r is equal to root 12 over pi, and I get the same exact expression as before. You understand? I can use this information to figure out the derivative, figure out the rate of change without explicitly solving the formula. So I am heavily utilizing implicit differentiation in calculating related rates. Here is another example, guys. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. Do you understand? So it's a very similar question, but now we're having a balloon. Can you see what's happening? The balloon, the amount of air pumped into it is 100 cubic centimeters a second. It means that the volume is growing by 100 every second. 100 cubic centimeters, yes? Constant growth of volume. You can already imagine the formula for the volume, correct, guys? It's simply 100 times t. Am I right? 100 times t. Yes, I'm not the only one that sees it, correct, guys? Right? At 0, you have no volume. 1 second later, you have 100 cubic centimeters, right? Every second you have, and by the same rate, even if it's the same rate uniformly, that means that in half a second you have 50 cubic centimeters and so on. Yes? So here is the situation, guys. The question is, and can you calculate it? How fast is the radius of the balloon increasing when diameter is 50 centimeters? Diameter, make sure you understand diameter. Let me remind you what is the formula for volume of a sphere. So volume of a sphere is 4 over 3 pi r cubed. You remember that? You need that, of course, because you need to relate volume of a sphere to the radius. Now, if you understood, please calculate the rate of change of the radius at the moment where the diameter is 50 centimeters. All right, guys? This example, please. We're doing the example, right? So what's in my screen, lower part of it? All right, I mean, guys, I don't know why it takes so long, but fine. Here is that formula. Let's do that together. Thank you, Humira. This is the situation, guys. So first of all, I'm having a video in which a sphere is growing. Do you agree? I mean, what really is happening here? The sphere is growing at a rate of 100 centimeters cubed every second. Agreed? And then if I watch this video, please tell me, what am I going to see? If I watch this video, what's happening? What are you seeing? In the simplest possible way to describe it, is that what you're seeing is a sphere that's getting bigger and bigger and bigger. It's getting bigger in volume at a constant rate. Agreed? It's just a video of a sphere that's getting larger, that's all. Here is the picture of that sphere. Here is the radius of that sphere. Here is the volume. Then I know that the volume of a sphere is 4/3 pi r cubed. Do you agree? I wrote you that formula. That's the formula for the spherical volume. I want to know with what speed is the radius growing. And not everywhere, but at the moment, I don't know where in the video, I pause at the moment where it happens to be that the diameter is 50 centimeters, which means the radius is 25 centimeters. Do you agree? I am pausing the video at the moment where the radius is 25 centimeters. And what do I get? Now let's now see what happens. I take the derivative with respect to time. You agree that volume is a function of time, and this is another way to write the volume as a function of time that involves the radius. You see the reason it's called related rates is because r, the growth of r is related to the growth of v, because they are identified by an equation. Yes, they are related by the equation. The related rates, the relationship is the equation that I constructed. So v is 4/3 pi r cubed. Now what's the derivative of v? It is 4 pi r squared dr dt. Here is my formula for dv dt. Yes, which is what? So dv dt is 100. It's 100 because it's always 100. And this part is 4 pi r squared dr dt. So dr dt is simply what? Dr dt, guys, we know dr dt is, I just move everything across, right? So it's divide by 4 pi, you get 25 pi. And divide by r squared, you get 25 over pi r squared. Are you following, guys? Yes, I mean, you see what I'm saying, guys. So such a question should take you a very, very little amount of time. I mean, this is as simple as it gets. I mean, the exam is going to be harder. And unfortunately, just people are not picturing the concepts well enough and fast enough to do it. But it should take you, what, 5 minutes at the very most. We can, of course, take longer if you stay in office hours. So, well, what happens then? So then I plug in, I want to know the rate when r is 25. So I plug instead of r 25, and 25 over 25 squared cancels one copy of 25. So I have 1 over pi times 25. You agree? So this is the rate of growth of the radius. Here is another example, guys. Okay, and here you can even, I'm going to leave this part here. So one of the classic examples is you have a ladder leaning against a wall. And this is an entirely fake ladder. The real ladder is much more complicated to analyze. So a ladder that is 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, you understand? So what's happening? So you can imagine the ladder, guys. So should I lean the ladder against the wall? And the bottom of it is moving. You see, here is the ladder against the wall, and the bottom is moving at a rate of 1 foot per second from the wall. You agree that if that is happening, then look, you see my hand? You cannot see the top of it, but as it happens, the hand, you can now, it's dropping, right? So the tip of the ladder is going to go down. And the question is, at what rate is it going to go down? When the bottom of the ladder is 6 feet away from the wall. Before you begin, guys, thinking about this question, what is it really mathematically about? If you had to illustrate in a video what is happening, you are seeing changing what? What shape are you seeing changing? Like in the first video, we saw a changing circle. In the second video, we saw a changing sphere. What is we are seeing here? What are we seeing here? Triangle. In particular, not just any triangle, but a right triangle. Can you try to solve this question, guys? I'm going to give you not a lot of time. I'm going to give you 4 minutes. That's all right, Darul. Thank you, Christina. All right, let's solve it together, guys. So here is what you are seeing. Do you look at it, guys? You're seeing a triangle. The hypotenuse is always 10 feet because that's the size of the triangle. We have vertical is y, horizontal is x. Yes? And then I drop this ladder down. And so the variables are x and y, and they are related. How are they related? Well, very clearly that x squared plus y squared equal to 100. Do you agree? X squared plus y squared always 100, because they always make the legs of a right triangle. And so I take the derivative, guys, of this. This I wrote 10, but I meant 100 here, right? So the derivative of d dx, I know it's 1 foot. So I take the derivative, it's 2x dx dt plus 2y dy dt equal to 0. Are you with me? Do you see where I got dx dt dy dt? Because x and y are not functions. I'm not considered, I'm not thinking about the x. They are functions of time. Yes? So what do we get? We get that dy dt, just solve this equation, is minus x over y dx dt. And dx dt is 1, so it's minus x divided by y. Do you see that? The ratio is minus x divided by y. Now I am interested in x being 6 feet. So x is 6 feet. If x is 6 feet, then what is y? Look at it. If x is 6 feet, then y is 10 squared minus 6 squared square root, so y is 8. So dy dt at 6 is minus 6 over 8, which is minus 3/4. Thank you, Christiana. Yes, guys? You understood how I solved it, yes? I mean, if you picture it, it's not hard to solve, but you have to picture it. So usually on the final, they have one question about related rates, but whether in class or on the online final, people don't tend to get it. Here is another question. A water tank has the shape of an inverted circular cone with base of radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 feet deep. Okay. Now, what is the volume? Here I'm going to give you this picture. This is the picture that you should have in your mind. We have a cone. You see, guys? The big cone is radius 2, height 4. Now, before I continue asking questions, guys, before we solve anything here, could you please tell me what mathematically is happening? As I move the time cursor forwards, you're seeing what mathematically? Like, remember, we saw a circle in the first example, we saw a sphere in the second example, then we were seeing a right triangle, morphing of right triangles in this example. What are we seeing here? Exactly, cone within another cone. So you see what happens here, guys? This is your question. Volume is again increased at a rate of 2 cubic meters per minute. We want to know how much is the depth changing here. Do you see that we have several quantities? What changes in time? The height and the radius are changing in time, but we're only interested in how fast is the height changing when height is 3 meters deep. Well, let's solve it together, guys. I don't have time, so let's do it together. So this is the volume, guys. The volume is 1/3 pi r squared h. That's the volume of a cone. Yes? Now, I do not like that r is there. R is a function of time and h is another function of time. Agreed? I just only am interested in relating h to the volume. And thankfully, you can see that the proportion of h to r, or r to h, basically r divided by h, is the same as 2 divided by 4. Do you agree? Those are similar cones. So 2 by 4 is the same as r divided by h. And that means that r is simply 1/2 h. And so my volume is 1/3 pi 1/2 h squared times h, or 1/12 pi h cubed. This first step is clear to you? I had several related quantities, several functions. We had r and h. I just wanted to relate volume to h. And this is what I have done. Good? And then now I'm going to take the derivative, guys. The derivative of the volume, dv dt, is 2. But the derivative on the other side is, just take the 3 down, it's 1/4 pi h squared dh dt. Any question at that stage? You see? And then I simply solve for the h dt. What is the h dt? I simply multiply everything that has everything in this side. I just multiply this by 4 and I get 8, and I divide by pi h squared. Now h is 3 for the purpose of my problem. H is 3. I'm interested in the rate of change, of the depth when the depth is 3. So what do I have here? I have 8. This is pi inverse. In other words, it's 8/9 pi. Do you see? I mean, this is what it squared this 3, so it's 9 pi. So it's 8 divided by 9 pi, and if I simplify, it's about 0.28 meters per minute. Good? Meters per minute. You can then think of the same questions, guys. You can go home afterwards and see if you can solve those questions without my assistance, but it should take very little time. I mean, you should train to answer such questions in 10 minutes. Or, I mean, get comfortable with the fact that you will not answer those questions. A man walks along a straight path at a speed of 4 feet per second. The Gesundheitsgestapo searchlight is located 20 feet from the path and is kept focused on the man to make sure he is a good citizen. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? How do we solve that question? You see, this is some sort of picture that I produced. So in other words, the searchlight, you see the man is walking along this line. Yes, of course, there is a big question, guys. Do you know what is Gesundheitsgestapo? Well, don't worry, you will soon know. Here is the distance 20 feet from the wall. And here is the distance that this person has traveled along that wall. And so what is really happening here, and here is the angle. The searchlight is turning to keep the laser focused on that man. Do you see this picture? So what's changing? X is changing, this length of the laser is changing, and the angle is changing. I'm only interested, and the man is walking, I think, at a constant speed. The man is walking 4 feet per second. This is that 4 feet per second. All right, so I am not interested in the laser. I'm only interested in knowing the length of the change in the angle. So what's the easiest way to relate the angle to just x, guys? Here, I know that this is 20, this is x, and this is theta. Would you please tell me what's the easiest way to relate the angle to x? What function relates in the right triangle this x to the angle theta? Very good. It should be tangent. So this is tangent of theta is x over 20. Do you see I avoided using this size because it's going to make it more difficult. The red line is definitely going to get longer. Yes, I want to just relate this x to the angle theta. So tangent theta is x over 20. I take the derivative with respect to time. And what do I get? I get secant squared theta d theta dt. Yes? And that would be what's that quantity? Secant squared of theta, guys, is what? If I take the derivative of the side across, it's 1 over 20 dx dt. And the dx dt is 4, so it's 4 over 20. It's equal to 1/5. And so d theta dt is I just divide by secant squared on both sides. So d theta dt is 1/5 cosine squared. And if I'm interested when x is 15 feet away from the wall, right, I can calculate what is that cosine squared, right? So cosine squared, if x is 15 feet, guys, so cosine is 20 over the hypotenuse, right? So the hypotenuse is 15 squared plus 20 squared, right? So cosine squared is what? Cosine squared is 20 squared divided by this length squared, which is 15 squared plus 20 squared. Upon simplifying it, it will be 16 over 25. So cosine squared is 16 over 25. So the answer is that the theta dt at x equal to 5 is 16 over 125 radians per second, or about 0.128 radians per second. You understand how I calculated, guys? It involves two steps: recognizing what simple thing is happening here, a very simple thing is happening here, and then translate it to a formula, and then take the implicit differentiation. So the reason it's complicated is that, first of all, people do not see the simple shape, and secondly, they are not as comfortable with implicit differentiation, right? But practicing related rates is practicing your imagination. It makes you see animations that are not presented to you, and they make you practice algebra once you do related rates. Sorry, once you do implicit differentiation. That's a thing that is difficult to people. Okay, and then here I try to explain, guys, how it's used in physics. You see, here are some explanations of how such ideas are used in physics. And I'm not sure how much I will go through it. It's optional, but I look how much I spend time to try to show you that you cannot do physics without those ideas. So even a simple motion of the spring relates to such ideas. Well, I suppose we can call it a day. Goodbye. Auf Wiedersehen. And if you have questions, you can stay after class. We can do something here. If you want to listen to what when we're a problem, stay with me. Otherwise, you had a long day. Good night. Thank you for coming. Okay, Christiana, let's hear the question from the test.